Once inside the facility, the transformation begins with primary processing. The goal here is not flavor, it is safety and structural preservation. Every movement of the automated rail system is engineered to reduce handling time. Less manual contact means lower contamination risk and more consistent product quality. Internal organs are removed through automated evisceration systems designed for precision. Why automation? Because consistency reduces accidental rupture of internal organs, especially the intestines, which could release bacteria. Mechanical precision protects both hygiene and the integrity of the muscle tissue. After internal removal, carcasses pass through antimicrobial rinse systems. These may use chilled, chlorinated water or organic acid solutions. The purpose is not to sterilize completely, that would damage the protein structure, but to reduce microbial load to safe, controllable levels before cooking. Rapid chilling is one of the most critical steps. Immediately lowering the internal temperature slows bacterial growth and stabilizes muscle proteins. As the carcass cools, rigor mortis develops a natural stiffening of muscle fibers. Controlling this phase determines tenderness after baking. Turkey muscle is composed primarily of myofibrillar proteins, actin and myosin. During cooking, these proteins will denature and tighten, expelling moisture. Understanding this microscopic structure is essential. Every industrial step before the oven aims to manage how these fibers will react to heat. Next comes inspection and grading. High-speed cameras and weight sensors categorize each turkey by mass and surface quality. Why is this necessary? Because thermal penetration depends on size. Grouping similar weights ensures that every bird reaches safe internal temperatures at the same time inside industrial ovens. Before seasoning or brining, excess surface moisture must be controlled. Air drying tunnels remove residual water. This improves brine absorption consistency and prevents dilution of seasoning solutions. Surface control now determines flavor balance later. At this stage, the turkey is clean, chilled, and structurally stabilized. It is still raw, muscle-dense, water-rich, and chemically reactive. In the next chapter, we will explore how industrial brining uses chemistry to manipulate protein behavior, locking moisture deep inside the meat before it ever reaches the oven. Brining is not just seasoning, it is controlled chemistry. Inside these stainless steel tanks, water is blended with precise concentrations of salt, phosphates, sugar, and natural flavor compounds. Each ingredient serves a scientific purpose. Salt begins the process of protein solubilization, while phosphates increase water binding capacity at the molecular level. When salt dissolves, it separates into sodium and chloride ions. These ions interact with muscle proteins, particularly myosin. This interaction loosens tightly packed protein structures, allowing them to bind additional water. The result? A turkey that retains moisture even under intense oven heat. Concentration is everything. Too little salt, and moisture escapes during baking. Too much, and texture becomes rubbery. Engineers monitor salinity, temperature, and pH continuously. Slight adjustments alter how deeply the brine penetrates the muscle fibers. In large-scale production, brine is not applied only from the outside. It is injected directly into the muscle using multi-needle systems. This ensures uniform distribution throughout the thick breast meat, something surface soaking alone cannot achieve. As needles inject the solution, pressure forces brine deep between muscle fibers. The liquid spreads along natural connective tissue pathways. This controlled infusion changes the internal water balance of the meat, increasing yield and reducing moisture loss during roasting. After injection, the turkeys enter vacuum tumblers. Removing air pressure expands muscle fibers slightly, allowing deeper brine absorption. Gentle tumbling evenly redistributes liquid while preventing structural damage. The vacuum also accelerates protein extraction, forming a sticky protein matrix that helps retain juices during baking. Notice the slight sheen forming on the surface. This is extracted myofibrillar protein. It acts like a natural binding gel. During roasting, this layer coagulates and helps seal moisture inside the meat. The final step in brining is time. The turkeys rest in chilled rooms, allowing diffusion to equalize salt concentration throughout the muscle. This resting phase ensures balanced flavor and predictable cooking behavior. In the next chapter, heat engineering takes over as controlled thermal energy transforms raw protein into golden roasted perfection. This is where chemistry meets controlled heat. Industrial turkey baking is not guesswork, it is thermal engineering. Every oven inside this facility is designed to deliver consistent energy transfer, ensuring each bird reaches safe internal temperatures without drying out. Unlike home ovens, industrial systems operate continuously. Turkeys travel through long tunnel ovens on synchronized conveyors. This allows precise control over time and temperature. Speed determines dwell time, the exact duration compression, each turkey remains inside the heated chamber. These high-velocity convection fans are critical. Heat transfer occurs through three mechanisms: conduction, convection, and radiation. In large-scale roasting, convection dominates. Rapid air circulation eliminates cold spots, ensuring even surface browning and uniform internal cooking. As surface temperatures rise above 140 degrees Celsius, the Maillard reaction begins. This chemical reaction between amino acids and reducing sugars produces complex flavor compounds and the characteristic golden brown color. It is not burning, it is controlled molecular transformation. While the surface browns, internal safety is monitored continuously. Food safety standards require the thickest portion of the breast to reach at least 74 degrees Celsius. At this point, harmful pathogens are effectively destroyed. Precision sensors prevent both undercooking and overcooking. As heat penetrates inward, proteins denature. Myosin begins tightening around 50 degrees Celsius, while actin